Yeah, let's start.
Okay. So today we'll be talking about a package in Python called TensorFlow, and this is used for machine learning, specifically deep learning. Maybe some of you have heard of that. Sure, you've all heard of artificial intelligence. It's all over the news now. But this is you know really getting popular. It's used in a lot of data analysis and a lot of different things that we'll touch on today. And so first, let me share my screen. Actually, what this works. Can you see my screen?
Yes, we can see it.
Okay, great. Okay, so yeah, this is be an introduction to machine learning using TensorFlow, Keras, and okay. Oops. Okay, so tensors are sort of like arrays, where from NumPy, the package that you've seen Dr. Ken use, but they're multi-dimensional arrays. Just like you can only create new ones, you can't change them. They're immutable, as they say. And so these are our the structures of our data that the TensorFlow will perform functions on. And so Keras is the actual programming interface that makes it easy to use for the user. They have the functions that are easy to implement and type, and so it's a lot easier to use this Keras, this API that they've created for TensorFlow. And so deep learning models are usually directed acyclic graph of layers. That doesn't make sense to you, that's okay, because this presentation has a lot of math in it, because I made this for a math class that I was taking at one point. And so Keras will build these graphs of layers and then run more efficiently on a GPU or TPU. And so the general machine learning workflow is we gather data, we explore the data, we prepare the data, clean it up, filter it, and then we'll build and train a model on that data. And then we'll try to get that model as optimized as possible, and we'll tune what they call hyperparameters. And then once we have everything working good, we can deploy this model on data that it's never seen before and make predictions. And so one of the popular examples is image classification. And there's this data set of images of items of clothing. And so, to download TensorFlow or, the package to install it, you would use pip install, like we talked about previously. And so, shown here, I would import TensorFlow. And, we can import it as TF to make it easier to type. I need NumPy. I need matplotlib to make plots, and then I need pandas for handling our data frames. And then OS is our operating system. We need to see what directory we're in or change our folder. And so we can easily download some of these kind of processed available data sets from the Keras database using this tf.keras.datasets. And then so we're working with this fashion MNIST. And so this is 70,000 images in their grayscale, as you can see. Kind of low quality, but you know, enough to get an idea of what each item is. And so here we split the data set up into training images and then the corresponding label, like is it a shirt or a shoe? And then we'll also have test images, test labels. And so the idea here with any kind of machine learning is you split your data into a training set where we'll train the you know, the model on that, you know, portion of the data, and then we'll have a test where we'll take our trained model and we'll see how it works on data that it's never seen before. And so our images are 28 by 28 pixels, and these are in NumPy arrays. And then so we usually do our split like 80% for training, 20% for testing. And then you can see there are 10 different classes here for the clothing type. Remember, Python indexing starts at 0, so it'd be 0, 1, 2, 3. And so a big thing that you have to do in machine learning is pre-processing or scaling your data. And so with image classification, such as this problem, it's going to look at the pixel intensity, right? So, and those range from 0 to 255, or there's 256 colors. And so we want to scale those from 0 to 1. So we would divide all of these images by 255 to scale them. And so in any kind of machine learning problem, you usually have to scale. And it's usually on, you know, scale from 0 to 1. And so here we're just looking at the data, making sure everything looks good, the labels are correct, right? Ankle boot, t-shirt, sneaker. And so for building the model, the most popular and kind of simple model is the sequential model. And so first we would flatten. So, right, we have a two-dimensional array, right? 28 by 28. And so we would flatten that into a one-dimensional array of 784 pixels. And then you add what's called a dense layer with 128 nodes. And so when I say nodes, we're talking about these kind of like these little circles. And then you want to remember that the number of nodes usually wants to be 2 to the, you know, the nth power, and that's more efficient for your processors. And then so our output layer, because we have 10 classes, we want 1 node for each class, and so we see this this last layer is for our output layer. And so each node on the output layer has a score for whether that's that image belongs to that category, right? Is that a shirt? Is that a shoe? And then so once we've got that all figured out, then we can compile the model. We use an optimizer, Atom being probably the most well-known and used. It's good for image classification and natural language processing. And so the loss function will compute the loss between the labels and predictions. you know, how good is it actually categorizing them. And then accuracy is going to judge how correctly it is getting those labels correct. And so for loss functions, since we have a multi-category problem here, like we have 10 different categories of coding, we would use a categorical cross entropy loss function. And so basically, it penalizes the algorithm or the model for a bad prediction. And so we try to reduce that loss by changing, the weights, or, changing the nodes basically, until we get a small loss. And so this is some of the math that I was referring to earlier. But basically, it's a stochastic gradient descent algorithm. And then we're trying to optimize this point. And so this is where like the math comes in.
Yes, ma'am.
Algorithm and machine learning. And so optimizer, like I said, Atom is the most common for image classification and natural language processing. And it's going to update the learning rate as it goes along. And it works in concert with the loss function to reduce loss by altering those nodes. And when I say weights, I mean, what are the values those nodes are given by the model. And then so activation function, and so this helps model for the interaction effects and nonlinear effects, because if our problem was a linear problem, it would be really easy to solve, but right, because we could just draw a straight line and say this image belongs to that class and the other one belongs to that class. But with deep, the whole thing with deep is that it's able to address nonlinear problems where multiple classes and they kind of overlap, and so that's where this activation function comes in. And so finally, when we have everything set up, our activation function, loss function, would actually fit our model, right, or train it. And so an epoch is one iteration over the entire data set. And then so we usually say how many epochs we want it to go for. And so as you see here, starting off with 1 to 10, our accuracy is around 82. And then as we move along, updates itself, we get up to around 91%. And then we would use the final epoch model to test on the test set. And so this is some images that it hasn't seen during the training, and we see that the accuracy is close, but it's less. It's around 88%. And then so this is a common problem in anytime you're training a model or fitting a model on your training set. It's called overfitting. It's where the model actually does better on the training set compared to the test set, because for some reason there's something in the training set that it's picking up on, and it's not able to do as well on data that it's never seen. So there are some ways to improve that, which will go around. And so we need to attach a what we call a softmax layer to convert these logits, these odds, to probabilities. And so if I predict for the first image in the test set, it's going to give me a lot of different probabilities, and you can see that these are all really low, right? These are to the 10 to the power of negative 8, 9, 9. But this last one is 0.994. So that would be, it's our model is saying that this last category or class, it's 99% confident that it's that class, and that class is a ankle boot. And so we see that our model was able to correctly classify this image as an ankle boot. And so it's not perfect, right? Our accuracy wasn't 100%. And so you can see like this sandal or this sneaker, it's actually a sneaker, but it was misclassified as a sandal. And so, you know, some images are hard to classify based on that low resolution, right? Even with my eyes, I can't really tell between a sneaker and a sandal sometimes. And so another popular, you know, problem is text classification or natural language processing. This is, you can see this in email where your Gmail account or whatever you use filters out the spam. Moderating on social media, product reviews, kind of, you know, like on Netflix. And so there's also sentiment analysis, whether you want to say whether this is good or bad, right? Based on its sentiment. And so for this example, we're going to look at some movie reviews and do sentiment analysis, whether the review was good or bad. And so, you know, similar to the previous example, you need to split your data set. And then, so this one is balanced with the equal number of positive and negative reviews. And so, again, you can download these data sets easily using this Keras utility. And so if we look at an example of a good review, right, we kind of see some words maybe that we can pick up. Good, right, great, superbly. And so if you want to format your directory, there's a nice function or from Keras that will format your directory for you. And if we look at a bad review, right, again, you can see that there are some words maybe that can be picked up as bad, you know, geez, stupid, stuff like that. And we're doing an 80-20 split of the training data, 20% for validation and testing. And so with text, you have to deal with punctuation, right? If it's HTML, you have all these, you know, different characters, quotation marks, percent, these, you know, arrows, carrots. And so, you know, you have to clean your data, kind of like scaling with the previous example. And then there's tokenization, which we're actually splitting the strings or the sentences into tokens. And then vectorization, we convert these tokens of, you know, words or word pairs, phrases, into numbers, because our computers love, you know, love numbers. So that's what we can input into our model. And then we can, you know, say how we want our vectorized layer to be, how many max tokens we want, what kind of output mode, batch size, how many, reviews are we doing at one time. And then we fit our pre-processing layer with adapt. And so if we look at text vectorization, we can see that our tokens, we would have to replace those with integer values, right, numbers, which we see here in this numpy array. And so if we look at, say, this token will just correspond to this word, lovely, and then this one will correspond to American. And then we apply this to our training, validation, and test data sets. And then so we have an embedding layer, which takes our integer encoded review and looks up the embedding vector for each word index. And so dropouts, like I said earlier, there are some ways that we can kind of prevent this overfitting. A dropout layer will actually drop. So in this case, it will drop 20% of the input just randomly. And that's a way to prevent that overfitting where it trains too much on the training set. And then pooling is a fixed length output vector for varying input lengths. And then so our 16 node layer and our last layer is single node. And so we'll compile our model. So in this case, we're determining whether the reviews are good or bad. So that's binary, right? So we'd use a binary loss function. Again, the atom optimizer. And we can train our model on, for 10 epochs. And at the end of our training, it's up to 88% accurate at determining whether this review is good or bad. And then so for the test set, it's around 87% accurate, which is, pretty good considering our training was around 88%. So there's a little bit of overfitting. And so we see that in this graph that if we train more, the more we train, the bigger our gap gets between our accuracy, between our training and our validation. And so we can say that, we can train for, however long we want. It's not really helping. It's actually getting worse. So we can use this early stopping function to stop the training before the validation accuracy levels off, right? Doesn't get any better. And this will prevent like that overfitting problem. And so we can export the model and save it and try it on some data that it's never seen, or some random phrases such as these, right? And so here's some different algorithms that you can use for machine learning. And so maybe some of you have heard of regression. It's where we try to predict the output of a continuous variable, right? There's linear, and it gets more complex, and polynomial or logistic, it's categorical. But basically it takes the the format of this y equals mx plus b, which you've probably seen, remember from algebra. And so in this example, we'll be using a gas mileage data set from the late 70s, early 80s. And based on certain features like number of cylinders, displacement, horsepower, we'll try to predict the fuel efficiency on certain cars. And then so again, we'll be using TensorFlow and Keras. Can download. So this data set is actually from kind of like a random machine learning website. But we would download the CSV. We can read that CSV with pandas, read CSV function. And then if we look at our data set, we see there's our miles per gallon and our different features. And then to clean up the data, some NAs where there's data is missing. And so for our categorical data, we use what's called one-hot encoding, because origin would be like Europe, Japan, USA, where it's manufactured. We would like a number instead, and so we're going to convert each of those instead of USA, Japan in the rows. We're going to make columns for each one, and we're going to say 1 would mean that yes, it belongs to that group, and 0 means that it does not belong to that group. So again, we'll do the 80-20 split on the data, 80% for training. And then we'll separate our target value, which in this case is miles per gallon, right? That's what we want to predict based on the other features. And so we have a large range for all these different feature values, right? Horsepower, weights, right? That's kind of a big outlier versus the other ones. And so we can use a normalization layer to normalize all the different features or different columns. And we can fit the layer to the data using DAPT. And basically normalize all of the layers. You see like 2125 will be our most likely our weight. You can see that it's all the values are now in a similar range. Okay, and then again, the sequential model for kind of simple problems like this. And we would normalize the input features and then linearly transform them to produce one output using the linear layer. And so we create our NumPy array, apply normalization layer to horsepower and build model. And so in this case, we're just using horsepower. And compile again using Atom Optimizer, and our loss function would be mean absolute error in this regression case. And then so for this one, we're doing 100 epochs for training. And so our training loss is around 3.8. Our validation loss is around 4.2. So it's actually higher. And if we check out our test set, we can see how well our horsepower correlates to our miles per gallon. And then this linear example, it's pretty good. You can kind of see this trend. And so this would be our regression line, but it doesn't capture this, these higher miles per gallon or even, these higher horsepower. And so with multiple variables, we can try to capture more of that, that pattern that we're looking for. So in this case, we're going to create a similar model. We're going to use multiple variables. And so if we compile and train for 100 epochs, our training loss and validation loss is lower than our single variable model, which is around 4. And so we're going to test and save that. And so if we use a deep neural network regression model, where we have all those nodes, like we showed earlier for the image classification. We can try to capture some of that curve in the graph that was shown earlier. And so we can see there's a lot more parameters here that are being looked at. And so we create a model, train for another 100 epochs, and we can see it does better for horsepower, right? You get that curve here, where we're able to capture that kind of those in the higher horsepower and lower miles per gallon. And that's because of our hidden layers. We're able to capture that relationship. And so if we use multiple inputs, not just the horsepower, we get a better result on the loss. And our lowest error will come from this multiple input deep neural network. And so we can save this model and use it on data that it's never seen before, or use it on some, and hopefully we get the same results that we got with our training data. We tested it. Okay, and so overfitting, like I said, is when we train on, well, it's when the model does better on the training data versus the test data that it hasn't seen, and it's actually picking up on noise or artifacts that are only visible in the training data, and so it doesn't do as well when it moves over to the test data. Underfitting, and so this is the opposite of overfitting. It's actually we're not training long enough, or our model isn't powerful enough, right? We hadn't add enough layers, not enough nodes. And so the key here is balance, right? We don't want to overtrain, but we don't want to undertrain, because we want our model to perform the best that it can. Ideal solution is to use complete data, so the model will generalize better. And the next best solution is to use regularization, where we're placing constraints on the quantity and type of information that the model will store. And so this is just going over the overfitting example that we saw earlier. And one way to prevent that is this early stopping function. We'll say, okay, our validation accuracy is not getting any better. So there's no need to keep training for more epochs, right? So we'll just stop early. And so this is another example where we're looking at basically data from simulated data from a particle collider, where we're trying to predict whether whether the data is real or noise. And so this is a very large data set, 11 million examples, 28 features. Right, these are all the different subatomic particles, and there's a binary class label. Is this real or is it just noise? And we do some cleaning of the data, repack into a feature vector, and then we're going to split the data into 10,000 batches, which is more efficient than trying to do everything at once. 1,000 examples for validation, 10,000 for training. From our batch size is 500. We're going to apply our batch size and shuffle and repeat for a training set to mix up the data, so it's not seeing the same set of data for each batch. And so the capacity would be the number of parameters the model is able to learn. More parameters equals more memorization. But the drawback of more parameters is the less likely the model will generalize or be able to be used on new data. But if the capacity is too small, right, we're going to be underfitting, and so it won't actually learn much. Our model will not be able to accurately predict. And so balance again is key. No standard for architecture of model. This depends on the data set, and so this takes some trial and error, some tuning, and it's known as a heuristic approach. Start small and build up. Right, start with a few layers and then increase the layers and the size of the nodes. And then you can stop when your validation loss levels off. And you can compare small, medium, tiny, large models. And we want to prevent overfitting. And so we can achieve better training by reducing learning rate during training. You can use early stopping to prevent unnecessary training. And so we have, in this example, for our small model, we have one layer with 16 units, right? That would be considered a small model. We have 481 trainable parameters. As opposed to a slightly bigger model, where we have 2 layers with 16 units. Now we're up to 753 trainable parameters. We start to see more overfitting. And then an even larger model would have 3 hidden layers with 64 units each, bringing our total parameters to over 10,000. And we see very early, often, our overfitting increases dramatically. And so for our largest model in this example, we have 4 hidden layers with 502 nodes, bringing our trainable parameters to over 800,000. And again, we see even more overfitting. And so if we just look at our network architecture, simple models are less likely to overfit, right? And we think bigger is better. It isn't necessarily so, especially in this example. In the context of weights, a simpler model is one in which the distribution of parameter values has less entropy or disorder. We can put constraints on network complexity by forcing it to give weights small values, thus distributing them more in a regular fashion. And so this is another way to prevent overfitting in our models. It's called regularization, and so we're going to, which adds to the loss function associated cost of large weights. And so there are 2 types: L1, which is weights stored exactly 0, which encourages a sparse model. We also have L2, and it penalizes weights parameters, but penalty goes to 0 for small weights. Does not encourage a sparse model. And so if we add weight regularization by passing instances to a layer as keyword arguments right here, for this layer, we're adding L2 regularization to those layers. And so every coefficient in the weight matrix of the layer will add 0.001 times the weight coefficient value squared to the total loss of the network. And right, so that's for each node in that layer, it's going to add a loss coefficient. And so this performs better than the original. It's more resistant to overfitting because it's not giving any one kind of node too much power, too much weight. And another overfitting prevention strategy would be dropout, which we saw earlier in the text classification. It's where we randomly drop out features of a layer during training. Dropout rate is the fraction of features to be dropped. Usually it's 20% to 50%. If we're testing, there's no dropout, right? It's that only happens in the training data. And so if we add a dropout to the large model of 50%, so for each layer we're dropping 50% of the data, we're not giving it to the model. It performs better. If we add dropout layers and L2 regularization, we see that our validation scores are even better, right? It's lower than our training. And so this is something called, hyperparameter tuning. And there are two types of model: influence the model selection, number and size of layers, right? We want a big model, small model, algorithm, learning rate, batch size. And so there's a built-in function for tuning these hyperparameters with Paris. And so if we define our hypermodel, it will actually go through different values, such as for our optimizer, or our learning rate 0.01, 0.001. And so we can let the program kind of optimize itself. And so we do we let the program tune itself, and it will tell us the optimal number of units in the first layer, optimal learning rate, and then so we can actually change those, and we can find the optimal number of epochs to train, right? How many, how long are we going to train? And so if we run our optimized model on the test data, we should see an increase in the accuracy. And so if you're interested in learning more about deep learning, machine learning, there are a lot of different resources out there. So Google is the creator of TensorFlow, and if you go to the TensorFlow website, there are a lot of tutorials and lectures about all about deep learning, machine learning, statistics. There's also Kaggle, which is another machine learning community. They oftentimes have competitions for who can develop the best model for this data set. There's also Hugging Face, which is another community similar to Kaggle. And so there's tons of examples and tutorials. And so if you're interested in learning more, I would recommend these websites. And so I'll stop sharing that. And so if we look at some more examples, let's see if I can find mine. Just give me a second. Okay. And so if we look at another example, something more, relevant to biology or clinical settings. And you probably heard about these, where deep learning or machine learning is used to classify, let's say CT scans, MRIs, or even, histological samples, from the clinic, right, where we're trying to predict whether this patient has cancer or, another disease, but typically it's cancer. And so in this example, I did some, image classification on histological samples from colorectal cancer patients. And so this data set is available on, from the Keras data set. And so we can load it. And so this is a multi-class classification similar to the items of clothing seen earlier. We're going to train on 80%, test on 10%, and validate on 10%. And so I did this originally on Google Colab, which is where you can use free resources, even GPUs or TPUs. That's sponsored by Google. And so we download the data set and we can split it into training sets, test sets, and validation sets. Takes a little while to download. And if we look at the number of classes, right, this is a multi-class problem. We have tumor, stroma, complex, adipose tissue. Here's an example of a debris sample, right? It's just kind of like random debris. And so all our samples are either, tumor, stroma, complex, they're all labeled, right? The histologist that took these samples, labeled each sample. And so we're going to try to predict on, say, some samples that don't have labels, which ones they are. So here I'm just declaring the batch size, image height 150 by 150 pixels. And so again, we're rescaling from 0 to 1 for pixel intensity. And so if we look at a basic model with 10 epochs, we can train, we can have 3 layers here with 16, 32, 64, and nodes for each layer. We compile it using our Atom optimizer. We're using our categorical cross entropy loss function because we have multiple classes. And then after 10 epochs, we get 83% accuracy on our test set. It's not bad. I mean, so 50% would be, flip of the coin. 82% is better than that. So it's working, but it could be better. And so if we look at our accuracy, we see that our validation accuracy is quite lower than our training accuracy. So that's overfitting. And our loss is pretty high, so we would still need to train more, but we don't want to overfit too much. And so we'll include early stopping to prevent unnecessary training in this round. our accuracy is 82%, so it actually decreased 1%. And so this is where we're kind of like in the tuning phase, right? We're trying different things to increase the accuracy, decrease the overfitting, decrease the loss. And so you can see there's still a large gap between our training and validation accuracy. So overfitting is still a problem. So let's see if adding a dropout layer could help with that, right? This is where we randomly drop some of the data to try to prevent our model from overfitting on our training data. And so if we do some training, the accuracy actually further decreased. So we see, okay, that didn't work. Let's not do the dropout. Let's try another approach. Overfitting is still a problem. And so there's another thing. If our data is a bit sparse, or it's not a large data set, we can try data augmentation. And so this is basically where we're taking the image, flipping it, rotating it, kind of just changing it a little, changing a little bit so that our model doesn't can see more data. It's but not like totally new or different data. We're just trying to increase the data set size and diversify it a little bit. And so if we use that approach where we're augmenting the data, we improve our accuracy up to 88%. And so that's pretty good. Anything over 90 would be kind of great. So 88% is pretty good. And we can see that this is actually decreased overfitting as well. Not only did we increase our accuracy, but we decreased our overfitting. This gap between the training and validation is diminished, and our loss is lower as well. And so it's all data set or case dependent. No one approach. Like if I tried this approach on a different data set, maybe the dropout approach would have been better. So this is where you kind of the tuning and trial and error comes into play. And then so this is another example of sentiment analysis using natural language processing. This is and so these are reviews from Yelp, right? So these are reviews of restaurants, whether the customer liked or disliked the restaurant. And so negative reviews are labeled as 0, and positive reviews are class 1. And so this would be a binary class problem. And so we split our data, we download our data sets, we split it. Here's just an example of a review. Right, we have to take all the words, convert them to tokens, and then we'll convert them to vectors or integers. And this is just showing, 3 reviews, each array embedded as these integer vectors. And so this is what our model is actually reading and trying to find a pattern from. And so here we're just using the simple sequential layer, the 16 node layer, and compile, put aside 50,000 reviews for validation. And then we're going to use early stopping, and we'll train. Looks like it didn't take very long to train. It stopped at around 6 epochs, and it's 94% accurate on the test set, determining whether this review was positive or negative. And so if we look, at we see some slight overfitting as the validation loss increases and validation accuracy decreases. As we look at our test, we can try to address this by using dropouts or that weight regularization where we penalize the different nodes. And here we're just graphing the validation loss and the training loss. You can see that our validation loss is increasing as we train more. While our accuracy tends to level off here. And so yeah, this model would definitely need some more tuning. This is kind of one that really didn't interest me very much, so I didn't spend much time on it. But I'm more interested in the kind of like the biological applications, such as clinical, trying to determine whether clinical samples are cancerous or not. Another example that I'm trying to currently implement in my studies would be looking at drug screening. How can we use deep learning for screening drugs, virtually screening drugs? And so if you're not familiar with virtual screening or molecular docking, this is where we take a receptor or a protein that we're interested in and trying to find drugs for, and we take a bunch of chemicals and we computationally try to fit them in the receptor, and we filter all through, it could be hundreds of thousands, millions. Now people are doing billions of different molecules, trying to find the best fit. And then, once we get some hits from that, then we would, validate those in the lab and seeing whether they actually, inhibit, say, SARS-CoV-2, or they kill cancer cells. And so, one of my projects is looking for drugs that targets, the certain receptors in breast cancer, such as the estrogen receptor or progesterone receptor. So if one way to use machine learning or deep learning in this example would be to say there are around there's like over 2 billion molecules that have been cataloged and that could be used as drugs. And so that's an extremely large number that would take a very long time to screen through all of them. And so the idea here is we make a little training set, like I showed earlier, and we dock our training set, a smaller, say around 1 million molecules on our receptor. And we can say, okay, we can do a binary class. We can say, okay, this group is good, these molecules are bad. And so we would do like 0, 1. And we can make a model to look at those molecules, and we could train our model to determine what's making those molecules good or bad, right? And then so once we get our model optimized, it's able to, predict a molecule will be good for this receptor, with high accuracy. And then we can use that model to filter out our larger data set, our billion molecule data set. And so, and that filtering is a lot easier to do than docking all billion of them, right? We can just feed it into our model and it'll say, okay, here's a subset, here's that are potential hits. So just go with those. And so that's the idea here, using deep learning with say molecular docking or drug discovery. And so if I do so I'm actually on our cluster right now. And so I just grabbed a compute node where we have GPUs available, which are good for deep learning. And I just told a script to run. So if this looks familiar, like we see here, the epochs, it's actually running training on some molecules. And if we go back up far enough, we can see here's our here's our layer, our input layer, or our layers, our hidden layer, with 100 nodes. We have a dropout layer, trying to prevent overfitting, normalization layers. And so what this model is doing here is it's training on molecules that I've already docked. That would be a training set. And so it's and that I've classified as good or bad. And so it's trying to figure out what makes those molecules good or bad. And so at the end here, our model is around 96% accurate at determining whether a molecule is good or bad for that receptor. And so, this is just one example of applying machine learning or deep learning to drug discovery or biology in general. And so that's an ongoing project for me. And so we just got a new application up and running for the cluster, making it easier for people with little experience working on the command line, like I did. You saw me over there just typing on a black screen, really not seeing anything else. And so this is called Open on Demand. And if you're interested in including or using the cluster for your studies, or you're just interested to learn more, and you want to increase your skill set, which I recommend, we can get you an account on the cluster. And an easy way to get on the cluster would be to use this if you're not comfortable with the command line like that. I mean, you still have to use the command line at some point, but this is a lot easier. So we have Jupyter Notebook set up, right? So I logged in. I just go here and I hit Jupyter Notebook, and
yeah, perhaps you can show them that.
Am I not sharing my screen? No.
Yeah, share your screen.
There we go. Okay. All right. So let me go back. So this is on demand. It's kind of like a portal to access the cluster. So like I said, we can get you an account, and you could all you have to do is type into a web browser and it will ask you to log in. And if you have an account set up, you can easily log in. And so we have Jupyter Notebook set up on here. We're waiting for RStudio to get set up. But basically, if I want to open a Jupyter Notebook on the cluster, I would just click this, and it's going to bring up my accounts. I can say how many number of hours I want to work, and I would hit launch. And so it's going to take a minute to allocate me a node, which is basically like one of the computers on the cluster. And in this case, I'm only using 1 core, but they do have 32 cores each. And so it's ready. When this button comes up, it's ready to connect. And so if I do that, I'm actually on the cluster now and in a Jupyter Notebook format where I have all my folders visible. And so this is an easy way, for people who are, not comfortable working on the command line to jump on to Jupyter. Like I said, we'll have RStudio soon. Even, you can do a kind of a Linux desktop, which is, similar to a Mac or Windows desktop. Just looks like this. And so, I'll still have, at some point, I'll still have to use the command line, but, it also has these, windows where I can look at, different, like programs that we have installed. And so say I want to look at a, a specific protein that I'm working on. I can, load it. Let's see. And so this offers a graphical user interface, or GUI as they call it. And so, like, I'm on the cluster right now where I can do stuff like this as well. If I need to look at my protein that I'm working with. And so this is a nice feature that we just got installed. And yeah, I think that's about it for my portion for today. Yeah, do you want to add anything else?
Yeah, maybe anybody has a question? Do we have questions?
No, sir.
Okay, thank you very much, Dr. Scott. Thank you so much for that, for taking your time to explain TensorFlow for machine learning. So please, I will advise everybody should please go back to that video and watch, right? Please, I'm telling you, machine learning is complex, but the basic is what you've touched, right? And one thing I also want to say is this: we are going to narrow our scope, right, on this machine learning stuff to drug development, drug discovery. Like Dr. Scott showed to you, we can have machine learning for diagnosis, for anything, right? But we want to narrow this to drug discovery, starting from next week, right? That's one. Two, we are working on a particular project, right? And before we go into that project, we want to show you a model using a model Doctor, we are going to do a general one for everybody to see. Then once you understand that concept, you understand that script, then we can take it further for everybody to have for groups, right? We are going to make it be in groups for you to have your respective project at the end of it, right? So that's going to be the plan. So I think, and Precious sent me, if I sent out assignment, no, I didn't later send out assignment to everybody because I just give you guys time to do more of practice. So I didn't later send out assignment to anybody. So that's the thing. So do you have any question?
No questions.
No questions, Dr. Do.
Okay. So
No, sir.
now, what Dr. Scott showed you guys something towards the end. You can use Anaconda on your laptop, but with our cluster, we have moved beyond Anaconda, right? So what I mean by that is, with the clusters, we already have a kind of application whereby you can run your Jupyter notebook, right? You can run normal Linux command. And then for Temi and then Menzoma that joined last year, I taught you Bash script. You can use that application for Jupyter notebook, Bash script. I think VMD, like Dr. Scott showed to you. Also, we're also working on R, right? So you can use that to run that. So I will advise everybody that are interested in taking this further to probably see me or Dr. Scott so that we can have you register on the cluster. So that's what I will advise. Yeah. So with that cluster, you can work on the cluster, not necessarily working on your own local computer. You can work on the cluster to do any kind of computation, any kind of studies you want to do. But like I said earlier, henceforth, we are going to focus and narrow down to how you can use Python, artificial intelligence, to design drugs, right? To screen for potential drug. You know, the last 2 years, or let me say last year, we did drug design basically using Chimera, all those softwares. But this time around, we are going to do drug design using purely Python programming, right? So that's what we are working on, and hopefully by next week, we should have it done. And we're going to do like 2 or 3 weeks of training on that for you. After that, then we are going to have you guys into groups, and you can work on your independent projects. So it's not going to be one person per project. No, it's going to be group projects. So I'm thinking we are going to have maybe like 3 to 4 groups, right? But that will come after we might have shown you, giving you an example of how everything works and how everything runs, right? Because I learned this LEAP program ends by November. So if it ends by November, that means we should use the month of September to look at those things, to show you the kind of project you want to do. So the month of October, then it will be for every group, and each group is going to work on their respective project. So that's the information I want to share with you. So that's going to be the all for this week. Yeah, because the school has resumed. So Dr. Scott and I, we have to stay behind on campus to make sure we have this done. So if there is no question, please, I'm not going to send any assignments. I want you to go and watch this, right? Learn 1 or 2 things from it. All right. Thank you very much, everybody. Thank you, Dr. Scott. Thank you so much.
Thank you.
Yeah. So
Thank
Dr.
you.
Scott,
Thank you.
Dr. Scott, please send me that script so that I can send it to the students, so that in case they want to do their independent practice, please send it to me. Yeah. And I'm also going to make the video available on that YouTube for everybody to see. Yeah. All right. Bye, everybody.
Take care, Dr. Do.
Bye.
Bye.
See, I hope to see you guys physically in the coming weeks. Even though Temi and Justina don't want to resume to campus.
We'll be seeing you, sir. Thank you.
All right. You guys should have a great weekend.
You too.
Thank you. You
Yeah.